Good. Okay, so it's a pleasure to be here, and it's really lovely to be back in Ambleside. CCPN here was my first conference many years ago, and it's so nice to be back and to be seeing people face to face again. So I want to follow on from Fabian to discuss ways that we can probe chemical exchange, to think about dynamics, particularly in slower timescales, involving titrations and molecular interactions and the formation of intermediate states, relaxation, dispersion, star measurements. So yeah, there's going to be sort of two sections to my talks here, but the thread between them is how we can use various sets of multiple quantum coherences to improve our measurements. So when we going to start thinking about titrations, when we think about titrations, we're considering the interaction of a larger molecule with some small molecule to form a bound complex. But I think NMR is really powerful, and you can pick up a lot more from these things. So your titrations are not just looking at these simple two-state interactions, but you can have more complex mechanisms. You can have an excited state and a ground state interacting, so conformational selection, or an induced fit where you have a conformational change after binding. And these, our lockdown dog aside, are important to mechanism. NMR titrations are really a very sensitive way to pick up some of these more complex mechanisms, and they can have really important biological consequences. I mean, the success of Gleevec as an inhibitor is down to a combination of a conformational selection and induced fit mechanism that was ultimately identified through NMR. So these are often not picked up by other measurements of binding, through ITC and so forth. So NMR is a really powerful way of doing this. And the question is, how do you look at your titrations in a way that actually gets the most out of this and can pick up these additional sorts of processes if they might exist? Okay, so when you're thinking about a titration, we're on the molecular scale, you look at a protein interacting with a ligand in exchange with a complex. In terms of the spins and nuclei, it's a two-state exchange between some state A and some state B that's got a forwards and backwards rate, which is going to depend on the ligand concentration. And depending on the frequency difference between the states, then you're going to, or the frequency difference relative to the exchange rate, you can see different phenomena ranging from slow exchange, and then as we increase the dissociation rate, you get through intermediate exchange to fast exchange. So the appearance of spectra, 1D case here as a function of exchange rate, will tell you not just about the KD, but also about the rate of binding. And in carrying that sort of kinetic information, you may have information about other more complex mechanisms. We can apply this in a straightforward way to fluorine NMR, which is very nice because it's a simple pulse-acquire experiment. You can introduce fluorinated amino acids into systems and use this to provide a pretty rapid assessment of interactions. This is a collaboration we had last year with the PLAB group. However, for 2D NMR, things are a little bit more complicated because you have to consider how we can define exchange regimes. What goes on? We have two frequency differences involved in the simplest 2D experiment. What is fast exchange? What is slow exchange in a 2D experiment where you may have a large frequency difference in one spin and a smaller frequency difference in another spin state? On top of that, 2D experiments, the appearance will actually depend very strongly on the pulse sequence. So this is an example. An HMQC would appear to have a different amount of binding than an HSQC experiment if you were to analyze this in a naive way, neglecting the effects of the pulse sequence. I'll come back to this in a moment. But also, exchange during 2D pulse sequences can give rise to what appears to be impossible cross peaks through the exchange of transverse magnetization in very simple experiments like COSY, but also in HSQCs, HMQCs. And we had a fun paper a year or so ago in collaboration with Tom Frankel at the Crick, where we looked into the origin of these. So I won't discuss it now, but it's for the NMR aficionados, it's quite a fun little problem to look at. So the approach that we've been working on over the last few years to actually analyze these titration data is essentially to build a virtual spectrometer, because we understand, as Fabian was demonstrating, we really understand the sort of spin physics that's going on underlying these things. So we can try and set up simulations that will then reproduce exactly what our experiments are doing, and then we try and optimize our parameters. In this case, not spectral densities, but our exchange rates and association constants that will fit our experimental observations. And this approach works pretty nicely. We can take our observed experiments and fit these. We can deal with overlap very nicely. And this is now wrapped up in a software package that we call Titan for titration analysis, which is being taken up by various groups around the world, which is good. And it's free for all academic users. It can be downloaded at NMR Titan. It's also an NMR box. And any industrial users, we have licensing options available. We also, last year, we just point anyone who's interested in doing titrations, we wrote a little methods article on just with some tips and tricks for recording titrations in an optimal way that makes them suitable for this sort of analysis. So, going back to the sort of details of what is going on with titrations and with these measurements. In a two-spin system, like an amide spin system, you have your single quantum frequency differences, your nitrogen single quantum frequency differences. And in an HSQC, this is what you're correlating. So you can be in slow exchange or fast exchange with relation to the proton frequency difference, or similarly with relation to the nitrogen frequency difference. And if you hit either of these frequency differences, then that's where you start to enter intermediate exchange, so your signal gets broadened out. That can be good in one sense because it provides information on the kinetics and on mechanism. On the other hand, if you're trying to follow your signals, then it can be a bit of a pain because you lose them from your spectrum. In the HMQC experiment, your magnetization is a combination of zero quantum, double quantum coherences during the indirect evolution time. So you are now comparing your exchange rate to the zero quantum frequency difference and to the double quantum frequency difference. These average out. Once you add them up together, they average out and you get a spectrum that looks like it's HSQC. But if you have intermediate exchange with respect to either the zero or the double quantum frequency difference, then you're going to get your signals broadened out. So the HMQC experiment is much more sensitive to broadening. And this is why, when I showed that example earlier, you have these systematic differences between the amount of binding that you would detect if you were just to analyze this in a naive way. The flip side of this is that you can perhaps take advantage of this and record an HSQC and an HMQC, compare these, try and see if you get similar results. Or indeed to record the HZQC spectra, to record an HDQC, so look at these individual zero quantum, double quantum transitions. These are pretty straightforward experiments to run. They've been around for a very long time, although they're not too widely used. The zero quantum is actually quite a nice coherence to look at because it's got a sort of semi-Troisi effect, so the lines can actually be a lot sharper than the HMQC or even the HSQC. Double quantum lines tend to be a little bit broader. So this was the idea that we had. Why not try and record multiple experiments during titration? Because, frankly, relative to the costs of preparing the samples, it doesn't take much extra time once you've got your compound in magnet, calibrated, shimmed, for an extra 10 minutes per sample. Why not record a couple more experiments? And this is what we did. So this was a collaboration with Ben Davis at analyse. We looked at the binding of a small molecule to the N-terminal domain of HSP90. We recorded this using HSQC titrations in the top left, HMQC in the top right, and then also these component zero and double quantum correlation experiments. And what we can see from this is that focusing this D93 resonance, the HSQC shows a little bit of broadening along the way. The HMQC is pretty strongly broadened, but the HZQC in the bottom left, now this is a zero quantum frequency difference, so the peaks are shifted. You have a much larger frequency difference in the indirect dimension, so you have effectively slow exchange. Whereas in the double quantum correlation spectrum in the bottom right, you have fast exchange because now the frequency difference is much smaller. So over a variety of peaks, this has a number of advantages. You can, in some circumstances, it would help you track peaks that are on the verge of slow exchange in some spectra. It might bring them back into fast exchange, so you can help assign them. And having these different spectra means that we can analyze these independently and determine the KDs, the K-offs, And we get 4 different measurements, which are all pretty consistent with each other. So this gives you a very robust assessment. And again, if you've got more complex mechanisms going on, then this is the sort of thing where differences might show up. You get a hint of what's actually going on. To record these 0 and double quantum experiments, we developed a new experiment based on the methyl SOFAST, or rather SOFAST. This can be applied to amides or methyl groups. So we use band-selector pulses to improve our sensitivity. However, we also applied a trick where we acquire all of our phase cycling initially without processing it. We can then recombine our experiments to form both 0 and double quantum components. So we get 2 experiments recorded simultaneously that we separate post-acquisition. These are sensitivity enhanced, so each experiment is just 1 over the root 2 the sensitivity of the HMQC, but you're getting the 2 experiments. Sorry, but you get the 2 experiments in the same amount of time. So it's a nice approach. It's very sensitive. If you really want, you can even shear the experiments and kind of combine them back up together into some sort of multiple quantum experiment, which is indicated in the red panel. So this was published about a year ago, so the sequences are available for download. If you download the latest version of Titan, they're provided with that. And it's quite a nice approach. They're pretty simple to record, and they're just regular 2D spectra to analyze and design. It's no trouble. So, in summary for this bit of the talk, I would just encourage folk to take a good look at your titration data. There's a huge wealth of information in these measurements that's often not extracted to the fullest extent. And given the effort that goes into recording these things and the interesting phenomena that can flag up, it's really worth people's time to try and get the most out of it. And I think being aware of the effects that single quantum, multiple quantum experiments can have on your spectra, and the benefits you can have if you try to compare these and extract additional information is just worth being aware of. So I want to switch tacks now and discuss the use of some higher order multiple quantum coherences for the analysis of excited states. So this is now considering a purely intramolecular equilibrium where you've got some dominant state A and an excited state B. So we now don't have the luxury of an external ligand where we can modulate the exchange. And so, Chris Waudby, next slide, please. This is where we bring in the whole panoply of NMR experiments that we've developed over the last few decades of CPMG, CEST, magnetization transfer, R1 row experiments, which are all adapted to various different timescales. What I wanted to look at is a slightly alternative approach, which is simply to consider the magnetic field dependence of the relaxation, the relaxation rates. So you have, when you're chemical exchange, you get a contribution to the relaxation rate due to that exchange, which in the fast exchange limit or fast intermediate exchange is proportional to the square of the field strength. So it goes up very rapidly. So the exchange contribution here is the PA, PB times the frequency difference squared divided by the exchange rate. We can write this in terms of sort of normalized chemical shift difference, psi, so you then have the exchange rate as the normalized chemical shift difference squared times the field strength squared. And that's valid up until you get to a sort of slow exchange when these things start to level off. So the idea is to measure some relaxation rates using Hahn echo experiments. So no fancy CPMG, it's just a simple R2 measurement at different fields and try and look at how these vary and try and interpret these. And we're going to do this in methyl spin systems. And methyls are great because they're very good for looking at large systems, but they have a very interesting set of energy levels because you've got 4 spins here that provide a lot of interesting spin physics. So you've got your carbon transitions, and then you have several different energy levels associated with the proton spin states. So you have the well-known methyl-Trozzi effect, is where you're looking at transitions involving these inner lines, where you've got one proton spin is flipping, and then the other 2 spins are opposing, so their dipolar contributions cancel out. However, we wanted to look at in particular the zero quantum and the double quantum relaxation rates. And again, we want to focus on these inner lines. These are the ones that form the methyl-Trosy effect. In the absence of external absence of external spins, these relaxation rates are zero. This is the methyl. These are the pure sort of methyl-Trosy resonances. We want to take care when we're measuring these to avoid the external lines, but there are pulse sequences that Art Palmer developed a few years ago that will nicely measure these relaxation rates. However, we were also interested to try and push this to the extremes of the spin systems and take advantage of some of these other protons that are around. So we can look at four-spin transitions, such as the quadruple quantum coherence that is indicated here in blue. So this is a coherence in which you're going from all of your spin states in the alpha to all of your spin states in the beta. So the protons are flipping, the carbons are flipping. There's a related four-spin double quantum transition in which the direction of the carbon spin flip is opposite to protons, which is very similar, and we're looking at that as well. And the really nice thing about these two transitions is they are also methyl-Trosy. Because the coherences involve all of the spins in the system, there are no dipolar relaxation contributions to any of these from within the methyl group. So we can calculate the relaxation rates that we expect for these states, actually using some software that Fabian published recently, RedKite. And the dipolar contribution to the relaxation of these four-spin states, the QQ quadruple quantum and the DQ prime, this four-spin double quantum, are not much larger than the classic zero and double quantum methyl-Trosy effect. So the only additional relaxation you get is through external protons that's a bit more sensitive. But given the extreme coherence, it's actually remarkably slowly relaxing. And the nice thing is when you think about chemical exchange, because you've got three proton spin flips going on at the same time, the sensitivity to relaxation and to chemical exchange is increased by a factor of 9 because you get three protons flipping. So this means that there are really sensitive ways to pick up on proton chemical shift perturbations. So the approach that we take is to measure various relaxation rates using Hahn echo experiments at different field strengths. So in the case of the zero quantum relaxation rate, we can then take the gradient of this line, and that is related to the psi c minus psi h. This is the difference in the normalized proton-carbon shift differences. We can represent this on the right in terms of a set of lines where these chemical shift differences are consistent with our observations. We can also do the same measurements with double quantum coherences, and this provides another set of constraints. However, we've got multiple intersections here. We can't uniquely determine the proton and the carbon shift differences or the relative shift differences because the exchange rates are wrapped up here. However, if we then add in these four-spin coherences, the quadruple quantum measurements, then we get a third set of lines, and we can then, from this, identify a unique intersection, at least up to an overall sign. There are always two solutions because this is the sign problem in determining the excited state chemical shift perturbations. And then, with the other four-spin double quantum transition provides us a fourth line, which gives us an internal consistency check. So we see that we have got this intersection point. So in doing these measurements, the idea is that we can then pin down, without having to do any relaxation dispersion type measurements, we get a measure of the relative proton and carbon chemical shift differences. This also provides a really nice way to identify whether you may have three-state exchange or more complex exchange. You only expect to get the overlap in the intersection of these at a single point where you have two-state exchange. If there is a third intermediate state, then there's no reason to expect that these lines would intersect. And so this can be a nice way to analyze and to try and detect whether you've got additional motions going on. And indeed, as I'll show later, to throw in these measurements together with other measurements to help constrain these more difficult cases. So we set about trying to measure these relaxation rates. As I say, Art Palmer published a few years ago pulse sequences to measure zero and double quantum relaxation rates. we've put together a sequence to measure the 4-spin relaxation rates. Again, we can play the same trick that we did for our simultaneous HZQC and HDQC experiment. And by recording all of our phase cycling separately, and then applying the phase cycles post-acquisition, we can extract both we can extract both double and quadruple quantum relaxation measurements simultaneously from the same experiment. So we get 2 for the price of 1. So overall, we have a 7-step phase cycle to select our proton coherence, and we have a 3-step phase cycle to select a carbon coherence. And from the combined 21-step phase cycle, we then get complex points for both of our 4-spin relaxation rates. So it's a really nice approach. Norbert Mueller termed it super experiments, where you do the phase cycling post-acquisition. And really, these days when hard drive space is cheap, there's no reason that you shouldn't, systems shouldn't routinely store these individual phase steps of phase cycles separately, so you can process these more easily. It would be really nice to see Bruker make this a little bit easier. So these are some of the measurements we have. This is for our favorite model system in John's lab, which is FLN5. This is a small immunoglobulin domain. We've been studying this for a long time in the context of co-translational folding. So it's also got a sort of fairly interesting set of dynamics and millisecond timescale motions. So it provides a nice test case. We can see that the 0 and double quantum relaxation rates on the left are reasonably slow. The quadruple and the 4-spin double quantum relaxation for I-743 are a little bit faster, but the relaxation rates are not that high given the coherence that we're talking about here, 40, 50 per second. For some other spin systems where you've actually got chemical exchange, the 4-spin relaxation rates can actually be slower than some of the 0 and the double quantum relaxation rates because of the cancellation of proton and carbon chemical shift contributions to relaxation. So we perform these measurements at 4 fields from 600 up to 950, and can see that we've got nice linear correlations here. So we can take the slopes of these, and we can then look to see, well, where are the intersections? What do we get? And we can see that these are really rather nice. So we get well-defined intersection points. The widths of these lines represents the uncertainty associated with the gradient. And we can, from these intersections, we then can identify our relative proton carbon chemical shift differences. This is exactly the sort of measurement you would want to be getting out of CPMG style approaches. However, what we do not have is the timescale of these motions. So we don't have any information on the timescales in the populations. This is all wrapped up together. However, we can combine these measurements with CPMG measurements. So we can do multiple quantum CPMG at a couple of fields. We can do a proton CPMG. Proton CPMGs are a little bit tricky in methyl groups. There is a nice single quantum experiment that's been developed. However, the actual magnitude of the dispersions you get tends to be quite small because proton shift differences are usually quite small for methyl groups. So the size of the dispersions, as you can see here, is often rather small. So the sensitivity is quite poor. But we can combine these together, and the red asterisks in the right-hand panel show the combined fit once you combine the Hahn echo together with the CPMG data. So we can analyze these jointly, and this provides you the best of both worlds. It gives us information on the timescale, but it also improves the accuracy and the robustness of our CPMG analysis. And it increases substantially the sensitivity to proton chemical shift changes. And we can see that on the structure, this actually identifies 2 separate clusters of exchange with 2 different timescales. So that sort of information, the timescale, is the thing that we wouldn't get out of these measurements by itself. But by combining the 2, we're able to get accurate measurements of shift differences, but also identify the populations and the exchange rates. We can also go a little bit further. We can consider the use of quadruple quantum coherences for CPMG measurements as well. There are a variety of CPMG measurements have been developed for methyl groups. the single quantum proton that I mentioned. The most popular experiment is a multiple quantum CPMG, looking at the combination of zero and double quantum coherences. This is great, it's very sensitive. It's quite hard to interpret because it depends on both proton and carbon shift differences. So you really need to get some additional information in there. Lewis's group published a few years back a triple quantum CPMG experiment where you look at the spin flips between your protons all up and all down. That's great because it gives you 9 times the sensitivity to small proton shift differences. However, the relaxation rates in these triple quantum coherences is really rather high because they all interact, they all get relaxed through a dipolar interaction with the central carbon. So the sensitivity of these measurements is very poor, which really sort of precludes the use to any reasonably large system. So we thought that the quadruple quantum relaxation rate would be a nice way to apply this. And actually, Fabian, just about 6 hours after we posted the preprint with the first Hahn echo measurements, was immediately asking, what about a CPMG? So we put the experiment together, and it works rather nicely. I'm not showing the sequence here, but it's fairly straightforward. And we can record this. The quadruple quantum CPMG is shown here in red. The triple quantum experiment is shown in blue. You can see that essentially the dispersion profiles are the same between the two. There are some small differences because the quadruple is also sensitive to the carbon shift change. In these two residues, the carbon shift change is quite small. The most important thing to recognize in this is that the base relaxation rate for the quadruple quantum coherence is substantially lower. This means the experiment is much more sensitive. This was recorded in I think a half or a third of the time of the triple quantum. You can use longer relaxation delays because you have a shorter relaxation rate. It will be applicable to larger molecules. So we think that this is going to become quite a useful complement to some of the other CPMG methods that are out there. So with that, I just want to wrap up. I hope I've shown that multiple quantum coherences in various forms are very useful to consider, both in titrations, but also for the analysis of excited states. And the rich sort of structure of the methyl energy levels provides a lot of opportunities to play around and to experiment and to probe new effects. And I think the fact that we're just starting to look at these quadruple quantum states, there's more to come. The fact that it's slowly relaxing gives us a lot of opportunities to play around and have a little bit more fun with these. So I hope that these methods that we're developing are going to become useful. We're certainly starting to apply them to larger systems, faster exchange that can't be quenched by CPMG. So then these sort of measurements become particularly useful. And with that, I'll just thank the folk who've been involved, particularly John, who's been supporting all this. This is our group a couple of years ago when we could all get together, and I hope we'll be doing that again. And thank you all for your attention.